Today we are going to build a neural synthesis model from scratch. The content of the model is going to be our anime sound effects. We are going to design those effects first. We are going to create a dataset and pre-process it and train it on our local systems. And then we are going to use a specific tool for latent space interaction. And yeah, it's going to be a 3-part project. I hope you're going to enjoy. So let's start. Before starting with all AI stuff, let's dip our hands in anime sound effect design. I know there are many quite good tutorials on the internet about how to make or how to design an anime sound, and we are going to follow base principle of those tutorials. We will take any sound source and drive it into a big reverb, then into a frequency shifter. And last, we are going to automate the frequency shifter frequency value to create these phrases, let's say motions. Okay, let's start with designing our first anime sound effect. I'm going to use phase blend for my synthesizer, but you can use anything or like any sound source. I will choose this noise effect and maybe shape it a bit for like a bit more percussion-y sound. Okay, maybe filter it a bit and also use another envelope to filter it out. This part is just my taste. You can also do whatever you want. Maybe more dramatic. Okay. Awesome. Nice. So we are going to add a reverb. We're going full, and for decay, I mean, it depends, but let's try with that. Okay, that seems fine. Maybe less dampening. Okay, bit more ringing, and we're going to add a frequency shifter next to reverb, and at last we need an LFO that we can create this motions over here. Or maybe, oops. Okay, maybe this is better. Oop. And use it unipolar. Okay, and it's going to be one-timed, maybe slower. Let's try. Okay, this is just a basic example for anime sound effects, this kind of like ringing tones. And deriving from that example, we are going to make many examples, sound effects, and yeah, that's it. Under normal circumstances, we sound designers tend to use reverbs, delays, those kind of time-based sound effects at the end of the effect chain. But this condition, we are going to use it as like a sound generator or creating a blurry wall of sound for our frequency shifter modulation. So it's time to go to my workstation. I will just create a new Tmax session, SSH to my computer, and yeah, as you can see, I have NVIDIA GeForce RTX 5070 over here. Is 12 GB VRAM, and after installing Conda, you're going to create a Conda environment. Which is, we are going to call RAVE. Python version, we need 3.9. And we hit yes. Okay, Now we can activate our conda environment, which we called RAVE. As you can see right now, our environment is indicated over here, and we can also check our Python version, which is connected, which is under our environment RAVE. After this, we're going to just install this assets RAVE package. This includes every package we need for that project. It takes a bit time. Okay, I think we installed everything we need. So the next is just, I have my data in this directory. As you can see, this WAV file, and I just created another path for pre-processed data directory, and we're just going to need RAVE pre-process which is I am created like an in path, and for output path it's basically the same thing, out path. And last we need to indicate that our channels are mono, and yeah, hit. So it's, our dataset is close to 1 hour and it created. So I can go outpath and let's see. Okay, let's see metadata, and also you can see this is our like sampler rate, and this is the n seconds of our dataset, and the data MDB is our compressed database dataset, and that's all. Now we are going to feed the pre-processed data into training, and it's going to take a bit. So we are going to cover how to evaluate the training process, how to monitor the process, and yeah. So let's start again the conda environment. I think it was in our outpath, the dataset, yes. So this is how are we going to start our training, RAVE train. In my case, I start with name, which is we are going to put this name, let's say version 1, and config file. There is a lot of configuration files. Maybe I can show you from the article that we are follow. As you can see here, like many different configurations for different needs. We are going to use version 1 because my graphics card has only 12 gigabytes of VRAM. And yeah, if you have like higher values or like faster graphic cards, you can choose other configurations. Configuration version 1, and db path is basically outpath in our case, and outpath, unfortunate naming, is, let's say, checkpoints. Okay, so I think it's also good to indicate the channels. And what else do we have? Yeah, we have like many different augmentations they introduced, but for this training I am not going to use them. And hitting enter, yeah, it started the training. So in this window you can see which epoch you are processing on, and like if you are using your GPU or like this CUDA environment and etc. And yeah, like what is your like sample rate of the samples, and what's the compression ratio, and like what's the receptive fields between these parameters. This is already good information, but we can have more. So we'll just open another Tmax window and SSH again to my but with this flag to open up a port, I think it was that, and we can just put like something number over here. Yeah. Yes. And let's clear out. Let's go to checkpoints. By the way, it's still running the training in other window. So we are just going to check. Okay. Our naming was anime version 1. So I'm going this version 1 version. Of course, we need to first activate the Conda environment again here. And yes, it's started. So when I go this localhost, yeah, and as you can see, we already finished this amount of steps. Yeah, like this is our epoch value. Maybe also you can see over here. Yeah, it's like already finishing 50th epoch. Maybe I can refresh it. And you can see the step count over here. So in RAVE model training, there is 2 phases. I can also show you this approach from this article. First phase called autoencoding phase, and the second phase called adversarial phase. And first phase takes about 1 million steps, and in my graphic card it takes about like 13-14 hours to finish 1 million parameters, and the rest is going to be about adversarial phase. But each step you can also hear the recreation of the sound with the model, and maybe I can show you it like that. Let's go here and close this. Go to a finished model. Let's say here, yes, go to tests and run this TensorBoard command over here and refresh it. Okay, so this one is a finished training, and you can see on this audio tab you can have like every, like, let's say 9 steps, 10 steps, you can hear how it sounds. After the first phase, you're going to see those kind of like adversarial charts or loss distribution charts, pred fake, prediction real charts. Let's change this color, it's awful. Yes. And I think this full band spectral distance shows the best. So in my finished training, I already finished like nearly 1.5 million steps and about like 5.8k epochs, and it took about like 24 hours. After you finish your training, you can go to the model's output directory and run this RAVE export command. You need to run this and name for your model. Let's say anime version 1. And an output directory for that. let's also say that to the main home directory. And this is also important to put this flag streaming true. This also ensures about when you are using with the nn tilde object in pure data or maxMSP, it's not going to click between these kind of like shifts of the samples. So yeah, we finished our model training. We went to the, yeah. As you can see, you can use this export in your maxMSP or pure data projects. So we are going to try that. After we exported our model, let's start with our beautiful nn tilde object. What we named our model is anime underscore version 1 streaming. You can also use different kind of flags over here for different needs. You can also see on this documentation, and like you can directly use forward and it's going to connect the encoding decoding lines accordingly. But if you want to also initiate some like parameter changes between this latent space, you can also use this approach. For to show, I will just use this encode decode section, and because it's like a pretty simple model, we have only 4 layers. So let's get a gain knob over here, and after that get a connection over here. Like normally this loop is sounding like that. And when we put it inside to our model, it's going to be transferred to the timbre of our model. And if I use my microphone for inference, as you can see, I also add this analog digital converter object over here, so it takes my audio, and here's how it sounds. I think it works quite good. This episode we are going to use this great object called nn.terrain. It's a tool for infer with the RAVE models. And yeah, maybe I can also explain it like that. So let's call RAVE gives us these 2 objects. This one is encoder and this one is decoder, and in both cases we are like feeding an audio into encoder, encoding them in like smaller count of layers, and with the decoder we are generating real-time audio within our model's timbres. So nn.terrain is basically gets into play in this part. So in our case, we have like 4 layers in this latent space, and nn.terrain just gives us enough endpoints with just 2D canvas. Also, you can use 3D parameters. Like today, I'm I have this drawing tablet, and it has pressure value as well, but I'm using on different purpose. With that two-dimensional pad, you can create as much as latent space parameters if you want, with some like another small model training. I don't know the deep explanation of it, but I will leave the link of the explanation and like this great overview videos of the project. And yeah, also I will leave some links to explain how you train these small models to infer. But I already prepared the terrain for myself, and I used again the same sound files that I trained. Yeah, basically in that case, like you can see the data out of it. Out of these like XY coordinates, we are just creating signals, and nn.terrain with those two signals create 4 signals for inferring array model. For the third parameter, I mean the pressure, I'm using it for changing the volume, because when I'm not touching the pad, I don't want to generate. Yeah, let's try it. Basically, what happens here, when I'm just moving my cursor around, those parameters are like changing, and those parameters inferring the model itself. So maybe I also have a bit more area to play around. And I also wanted to try another thing with that. There is an app called, Zixim. I'm using the pro version, but you can also use the free version of it. If you are like connected to the same Wi-Fi or like same local network with your Max device, you can type down the IP address of the computer and the port number that you select, and you can send OSC messages into the Max from the sensors of the phone. So I basically choose acceleration and gyro sensors of this old phone, and as you can see, like these parameters are like static right now, but when I hit to the play button from here, as you can see, I'm started to sending those accelerometer then gyroscopic data, and you see the parameter changes in this. And with that parameters, I have like 4 parameter changes, and let's try that as well. Yes. Let's test. Yeah, it's another playful and creative way for infer the RAVE model. I think now I am done with the demonstration of these tools. If you're also interested, please check the nn.terrain documentation. There's a lot of great explanations how to train a model for the nn.terrain. Okay, thank you for watching. I think next week we are going to find a different project to go on. Hope you enjoyed it. Thank you so much.